Well, good afternoon and happy Monday. So as I mentioned, what I would like to do today is a short review on the risk assessment portion of the FA. So this really is a section referred to as health hazards and risk assessment. We'll cover today dose response toxicity. We'll look at both carcinogens and non-carcinogens, and we'll look at exposure routes and pathways and ways of actually calculating the risk due to environmental contaminants. We will not cover occupational health. We've covered a little bit in class on protective equipment. If there's interest, at some point, I could put together a review of the occupational health portion of the FE. So I posted this same quote in 489 earlier this semester, and it's just remembering that what is a poison depends on the dose. So we'll talk about hazards. So hazards are the probability of an adverse effect of a particular situation, and a risk in this context is a measure of that probability. And we talked about exposures in 483, and just a reminder that when we're looking at occupational exposure, the assumption is that those that are exposed are whole, healthy adults. We're not dealing with children. We're not dealing with or protecting the immunocompromised or the elderly. We're focused on protecting those that are whole, healthy adults. And then the other assumption is that these adults are exposed only during the workday. They're able to move from that environment so that they are not exposed the rest of the day. When we look at general environmental exposure limits, we're looking at protecting the most vulnerable. So we're looking at protecting infants, the elderly, those that are immune compromised. And the assumption is that there's no escape from that exposure. So it's in your environment, it's in your breathing zone, or it's within your drinking water, but you don't have an alternative to prevent or to avoid that exposure. So when we talk about dose, we're talking about the total mass of a substance to which the body is subjected. And dose, as it mentions here, is a function of the concentration, how long you're exposed to that substance, the rate of introduction into the body. So depends whether it's an ingestion. So how often are you consuming it? Or how much are you breathing? And typically it will be in the units of mass of the substance per mass of body weight per time. So this is the substance. This mass, though, is the body weight, and it's averaged over some period. The response is the physiological changes that are produced by that toxin. So, for instance, with Pozo Roca in Mexico, it was a H2S. The exposure was breathing. In other cases, the exposure could be dermal. And it's how does the body respond to that toxin? We also talk about acute versus chronic. Puerto Rico was an acute exposure, sudden event, typically short term, and it results in some sort of sudden damage as a result of that exposure. Bhopal was an acute event. And the measure of toxicity could be organ injury. It could be coma, so exposure to excess concentrations of carbon monoxide can result in a coma, results in death. That's an acute exposure. Chronic exposure is that exposure that occurs over a long period of time, and it results in accumulated damage from repeated exposure. So if you're looking at, for instance, silicosis, the repeated exposure to silica in mining, that is a chronic exposure because it's occurring over a longer period of time. Typically, when we look at cancer, that's a chronic exposure. It's long-term exposure to a particular toxin. Feel free to stop me at any point, post a question in the chat, or simply unmute yourself, and happy to answer any questions. We can also talk about, with terms of toxicity, we can talk about local. So it's specific to one organ. So perhaps it causes some, Cerveso, Italy, caused chloracne. So it was the skin that was affected. And the skin is an organ. It could affect the lungs, but it only affects the lungs. Systemic means that the effect is distributed out through the body. So it affects, for instance, the lymph nodes and the lymph system. So it's affecting the entire body. And then we talk about chemicals that are carcinogenic, that induce cancer, chemicals that are mutagenic, that result in some sort of mutation of genes or chromosomes. For instance, UV light can cause mutations. Teratogens cause defects in the developing embryo or fetus. So these actually have a significant effect on the developing embryo or fetus. And back in the 50s, and I forget the name of it, but there was a drug that was actually prescribed to try and reduce nausea in pregnant women. Turned out it was a teratogen and caused significant damage to the fetus, loss of, basically lack of development of limbs, before it was finally taken off the market because of its effects. So when we're looking at risk assessment, it's a multi-step process. So we need to collect data. We need to evaluate that data. We need to identify, are there hazards? So what are the potential contaminants? Project One, you did this with looking at various different equipment that is used and had to look at, well, what were the potential contaminants? What are the concentrations of these contaminants? How toxic are they? So we get into the idea of dose, then we get into the idea of toxicity, so how toxic, and then what is the potential exposure? So we'll talk about the routes of exposure, but how can an individual become exposed, or how can any organism become exposed? How long are they exposed for that? And obviously at what levels? And then we get into the risk characterization or quantification. So we're trying to quantify the level of risk. And then finally, we're looking at managing that risk. How can we prevent a person from becoming exposed? So for instance, many years ago, I worked on a site that was up in Marquette. It was an old foundry. And they were building condos on this site. So what they had to do was go through and they had to look at what were the contaminants, what were the typical doses, how toxic were those contaminants, how could people be exposed to those, then characterize the risk, and then manage the risk. This was actually, this site that I worked on was the first limited residential closure that was done in Michigan. And the decision was made not to clean up to residential standards, but to use protocols and restrictions on the site to manage risk. Basically, one of the things that had to be done was that people were not allowed, and it was in the deed there was a deed restriction that people were not allowed to garden. Why? Because it was concerned about contaminated soil and the plants taking up the metals in the soil. There was ventilation systems, talk about vapor intrusion. This vapor intrusion system placed, or extraction system placed in the basements in order to mitigate any potential exposure to organic solvents. So these were part of the deed restrictions in order to allow it to be cleaned up to a limited residential standard. So when we're looking at routes of exposure, basic routes are inhalation, ingestion, and absorption through contact, which is typically dermal or through the skin. So when we're looking the other way at the media, when you're looking at groundwater, obviously people can ingest that if it's drinking water. They can come in contact with it through dermal contact, typically when they're showering or bathing, or if that groundwater is used to fill a swimming pool. They can inhale any chemicals that are transferred to the air during showering. Same thing with surface water. Sediment, we're looking typically at ingestion or dermal contact. So little kids potentially eating soils and sediments. So you see soils and dust, same thing. Air, we're typically talking about inhalation. And then food, typical route is ingestion. So set this one up as a poll. Typical type of question for the FE, they're all multiple choice. And this question, are the questions on the FE multiple choice? And yes, all of the questions on the FE are multiple choice. And I have a number of problems in here. All of the problems are actually written in an FE format that we'll go through. So the answer is food. Be careful. Things like accept. So in general, dermal contact is a route of exposure for each of the following media except. So remember, groundwater, dermal contact is possible in the showering, mentioned if it's used for swimming, but mainly showering and bathing. Surface water, the same thing. Soil can, if you're actually playing in the, children are playing in the soil, they can be contacted on their skin. Typically, food is not. So the answer, according to ABET, number of other definitions that are used are given here. The NOAEL is the no observed adverse effect level. And then the reference dose is an estimate with uncertainty, spanning perhaps about an order of magnitude of a daily, typically it'll be for oral exposure to a human population. And that includes the sensitive groups, because remember, here we're looking at environmental exposure that's likely not to result in appreciable risk of deleterious effects during a lifetime. So there are a number of things. We're looking at lifetime exposure. We're looking at protecting the sensitive populations. We're looking at no observed adverse or likely not to achieve a deleterious effect, and this is for human populations. The reference dose or an acceptable daily intake is that NOAEL divided by an uncertainty factor, and that uncertainty factor is related to species. This is really for humans. How sensitive is the population, or how sensitive are different populations? How much information do we have about that particular toxin? And then we can use that to assess the risk. And we'll go through an example with that. So you can see on these plots, these are dose response curves. And you can see, for instance, comparing compound A and compound B. And this is done as a mortality, so it's cumulative percent mortality. And from this, you can determine what the dose would be that would result in 50% of the population dying from that exposure. And that is referred to as the lethal dose 50. You could do the same thing for lethal dose 75, lethal dose 25. Typically, lethal dose 50 is what's used. The other uncertainty here is that we don't test these chemicals on humans. So typically, we're looking at animal studies, and then we have to relate those and try and relate those to humans, the effect on humans. So that's a significant uncertainty right there. And you can see here this no observed adverse effect level. And you can see in this other plot how different populations are impacted. So you have a population that's hypersensitive. So there, if we were to look at the lethal dose 50, it will be less than what we would have for the mean and less than a population that is less sensitive. Again, this all adds to the uncertainty that we have to deal with. The chronic daily intake is the mass that is consumed, and this is typically its mass, for instance, in milligrams, per body weight per day, so per ton. And typically it would be per day. What we refer to as the hazard quotient is the CDI for a particular chemical divided by the reference dose for that chemical, and the hazard index is the sum of all the hazard quotients. So if there's multiple contaminants, then you're looking at the sum of those contaminants. So in this situation here, we have a person that's exposed to 3 chemicals, chemical A, B, and C. The chronic daily exposure, so this is the CDI, has been calculated. And the RFD is provided, that chemical. So we can calculate the hazard quotient and the hazard index. And again, this is the same format that you would see on the FE. The hazard index is most nearly, it would be 0.04 divided by 0.07. So that's a hazard quotient for A, plus 0.08 divided by 0.16, plus 0.2 over 0.35. And that is equal to 1.51. That is greater than 1. So that tells you that, yes, this is potential hazard. So this is of concern. If it's significantly less than 1, then it is likely not to be of concern. So we have a similar problem. I've done it as a similar format. So a hazard index of 0.001 implies, so in terms of the first answer, the hazard index is not a measure of risk. So you cannot take, for instance, this hazard index, which is 1 in 1,000. That does not mean that there is a 1 in 1,000 probability of an event occurring. It does not measure risk. Okay. So don't relate it to risk, don't relate it to probability. Remember, the hazard quotient is equal to CDI over the RFD, the reference dose. Okay. So if the hazard, we sum the hazard index quotients to get the hazard index. So here, if you think back at that previous example, the RFD is actually larger. In order to get a very small CDI, the RFD has to be much greater than the CDI for this situation. So the answer is that there is little concern for the potential health effects. That's the conclusion that you make from that hazard index. So I've mentioned some of these before in terms of the limitations of all of this, in terms of species. We talked about sensitivities, mechanisms vary. That means that much of what we actually have in the way of assessing risk to human populations is based on epidemiological studies. That's when an event happens, and then we try and go back and figure out what was the effect. So how did what happened to that population? And that's really difficult because often, especially for instance with cancer, we're talking about a long latency period before we see an effect. There's so many other things that have happened along the way. People don't recall what their exposures were, which makes this very, very difficult. And this really adds to this uncertainty with all of this analysis. So when we look at kind of moving to carcinogens, when we look at the process of cancer developing, the general belief is that it occurs in stages. So, for instance, initially, there's this initiation process. So there's some irreversible lesion on the DNA, and that will lead to cancer if subsequent events happen. So in itself doesn't necessarily result in cancer. There needs to be some subsequent events. And that includes the next stage, which is promotion. And those are the biochemical processes that accelerate the promotion. So you have an initiation, some impact on DNA, and then this promotion that accelerates the process, and then the progression, which is the unmediated growth of cells and the formation of a tumor. There are multiple models. So for instance, one is the multi-hit, which says that a single dose, for instance, of radiation is enough to cause irreversible damage, resulting in ultimately cancer. Multi-stage says that the cell line has to pass through multiple stages before the tumor is initiated. The linearized multi-stage is what EPA uses. And it assumes that there's some dose that is related to the effect. And it's a linear relationship. So there's some, if it's linear, there's some, as we increase the dose, we increase the risk. Think of it that way. And then multi-hit says that there has to be a certain number of hits before. So for instance, UV, you have to have a certain number of times where this DNA is exposed to UV radiation before you see an effect. So as I mentioned, EPA uses a linear multi-stage model, which means that you have to have multiple events happen, and the risk decreases with decreasing dose, or increases with increasing dose. But there's some risk no matter how small the dose. So there's no dose that is in effect completely and totally safe with zero risk. The relationship between the risk and the dose, or the chronic daily intake, is assumed to be a linear relationship with a slope, and that slope is the cancer slope factor or the potency factor. And you can see that in this figure here, we're looking at lifetime risk versus the chronic daily intake. So there is some risk. It's never really zero. It may approach zero, but it's never truly zero. And that risk is based on the exposure. So this involves calculating this chronic daily intake. And it is dependent, and I didn't change this. So the chronic daily intake, for instance, from drinking water, is equal to the contaminant concentration in water times the ingestion rate times an exposure frequency times the exposure duration divided by the body weight times an averaging time. This is the approach that has been used to calculate almost all of the MCLs for drinking water. And what the assumption was that when they do the calculation due to cancer, the acceptable level of risk is 1 in 100,000 to 1 in a million. So what is determined is that it's 1 in a million, that there is one excess cancer per million population due to exposure, lifetime exposure to that chemical in drinking water. And most of the MCLs for drinking water have been determined based on ingestion alone. So they have not looked at inhalation. We can do the same for air. Now we're looking at the air concentration, but now we're looking at the inhalation rate, not the ingestion rate. And again, we'll use an averaging time. So for carcinogens, we use an averaging time of 75 years. So it's a lifetime exposure. And for non-carcinogens, we use the exposure duration. And you'll see that in the examples. This is from the FE reference handbook. So this is the table that's given for calculating the chronic daily doses or the adsorbed doses for dermal contact for the various exposure pathways. The FE reference handbook also gives you the various parameters that you need for these calculations. note, these are not in the environmental engineering section. They're in the safety section of the reference handbook. So recognize that when you're taking the FA, you're not going to find everything you need in the environmental engineering section. So let's look at this. Suppose we have an industrial facility. It emits benzene in the air. The concentration of benzene in the air in the residential neighborhood surrounding the facility is measured at 0.01 milligrams per cubic meter. Determine the chronic daily intake of benzene by adult men living in this neighborhood. And typically you will say the answer is most nearly, and then you're given some choices. So the chronic daily intake is equal to 0.01 milligrams per cubic meter. From that table that I just showed you, the inhalation rate is 15.2 meters cubed per day times 365 days per year. And the table also states that the typical time that someone resides at a home is 30 years. So 30 years is the duration. And note, meters cubed cancel, days cancel, years cancel, and we're left with milligrams. We're looking at benzene, which is a carcinogen. Average weight for adult men is 78 kilograms. We're averaging, because it's carcinogen, at 75 years and 365 days per year. Years cancel, and that is equal to 7.8 times 10 to the minus 4 milligrams per kilogram per day. So that is the chronic daily intake. I put in a slide here, which I haven't used, but you can see here the appropriate data that you would need for this calculation. To calculate the risk, that is your CDI times the potency factor, or the slope, the cancer slope factor. So to calculate this here, your chronic daily intake is equal to 0.04 milligrams per liter. So drinking water, average is 2.3 liters per day. That we're looking at 45, we're told in this case that it's 45 years of exposure, 365 days per year. So years cancel, days cancel, liters cancel. Again, we have milligrams. We'll divide by the average weight of an adult female. Average for cancer, 75 years, 365 days per year. Years cancel. And again, we have milligrams per day, and that is 8.4 times 10 to the minus 4. And milligrams per kilogram per day. And I should have corrected this and I didn't, so I've got it calculated for the CDI. And let's just say instead this asks for the CDI is most nearly, and that would be incremental risk is your toxicity times your exposure. So we'll multiply the CDI times the potency factor, or the slope factor. The same thing. Okay. I'm going to skip this one because we've basically done. Now, the difference is when you calculate the risk for a non-carcinogen. So this, everything we did before was for carcinogens. This is for a non-carcinogen. So in this case here, we have a 2-year-old child plays on vacant land that was once a small industrial site. The child is playing 5 days per week for 3 years. On average, the child is ingesting 200 milligrams of soil per day, and the soil contains Chrome 6 at a concentration of 2.1 milligrams per liter. It's non-carcinogen. So now when you're looking at the averaging time, you will average using the exposure time, not the lifetime. So 200 milligrams per day, and that's milligrams of soil that's consumed. Concentration of 2.1 milligrams of Chrome 6 per kilogram of soil, milligrams and kilograms. So we need to convert here. So now kilograms cancel, milligrams cancel. The child is playing 5 days per week. We're going to assume 52 weeks per year, and is playing for 3 years. So years cancel, weeks cancel, and days cancel, and we're left with milligrams of Chrome 6. We'll divide that by the average weight of a child that is between 1 and 5 years, so 16 kilograms. The exposure time is 3 years and 365 days per year. So years cancel, and we're left with milligram days in the denominator, and that is equal to 1.87 times 10 to the minus 5 milligrams per kilogram day. So the RFD for Chrome 6 is given as 3 times 10 to the minus 3. So the hazard index, and because of time, I'm not going to pull up the poll. The hazard quotient is equal to the CDI divided by the reference dose, and that is equal to 0.062. And if we assume that the only contaminant present is Chrome 6, then the hazard index equals the hazard quotient. Hopefully this helps to give some sense of the type of questions that you might see on the FE related to risk and definitions